Hi everyone, this fourth part on the op-amp will be dedicated to the analysis of some active filters. These filters are important because they are used in many circuits. For example, they are present in spectrum analyzers, such as this one for which I give a complete tutorial on how to build it. You can find the link in the description of this video if you are interested in making your own. They are also present in EMG circuit sensors. For example, here is a prototype that I designed which allows me to shoot in a video game simply by closing my hand. You will also find the link to a full tutorial in the description of this video if you are interested in building your own. So, a filter is a circuit that is meant to modify the amplitude of a signal depending on its frequency. Usually, the filter changes the phase too. A filter is said to be passive if it operates by using the energy from the input signal. It is said to be active if it needs an external supply of energy for its operation. Active filters offer more flexibility than passive filters, so they are the ones that we are going to analyze. We cannot discuss all existing filters, so here we are going to focus on an example of each primary type of filters: the low-pass filter, the high-pass filter, the bandpass filter, and the bandstop filter, which is also known as the notch filter. Let us start with the low-pass filter, and in what follows, we assume that we are injecting an input voltage of the form A cosine omega t, where A is the amplitude of the signal and omega the angular frequency. By the way, we are going to work with complex numbers and impedances that we discussed in a previous chapter, so go check in the description of this video for the link to this chapter if you need to refresh your memory. You should notice here that the circuit is very similar to an inverting amplifier. The only difference is that a capacitor C has been added in parallel to the feedback resistor R2. So we don't need to analyze again the op-amp circuit. We can directly write that instead of V out equals minus R2 over R1 V in, we have that the complex output voltage is equal to the negative of the parallel impedance Z2 formed by R2 and C, divided by R1 times the complex input voltage. Note that all complex quantities here are indicated by a tilde on top of their labels. So Z2 is obtained by taking the product of the R2 and C's impedances divided by their sum. As a result, we find that the complex output voltage is minus R2 over R1 1 plus JR2C omega times the complex input voltage. Now we can define the complex voltage gain as the ratio of the complex output voltage to the complex input voltage. So G tilde is given by minus R2 over R1 1 plus JR2C omega. I assume here that you know how to express this quantity in exponential form. If you don't, just watch again the previous chapter on complex numbers and impedance. So, we can write G tilde as G times exponential J phi, where G is the modulus of the complex gain and phi is the phase. And you should easily find that G and phi are given by the expressions that I'm showing here. Note that sometimes I may call G the real gain of the filter because it is a real quantity, but pay attention that it is the modulus of the complex gain and not the real part of it. So, using the exponential form, we find that the complex output voltage is Ga exponential j omega t plus phi. So we easily obtain the real output voltage by taking the real part. The result is pretty simple. The amplitude of the signal is multiplied by G, the real gain, and its phase is shifted by phi. You can check that phi in this case is always positive, but smaller than pi. So this means that the output signal leads the input signal. By looking at the expression of the real gain, it is easy to see that it is maximum when omega is 0 and 0 when omega is infinite. So we find that the maximum gain is R2 over R1 at 0 frequency, and then the gain decreases down to 0 as the frequency increases. So this confirms that what we have is really a low-pass filter. So the low-pass filter lets low frequencies pass and blocks high frequencies. But what do low frequencies and high frequencies mean? We need to set a convention for what we consider to be a passing frequency and what we consider to be a blocked frequency. The general convention is to define the cutoff frequency as the frequency for which the power gain is half of its maximum. Understand here that this is purely conventional. It would be totally acceptable to define it as the frequency for which it is a voltage gain that is half of its maximum, or the voltage gain is 1/10 of its maximum. The reason why we choose to define it in terms of the power gain is that power is usually what matters at the output of a filter. For example, in an audio filter, what affects our ears is not directly the voltage, but the power, that is, the energy per unit time, because it takes some energy for the sound waves to excite our eardrums. And why do we choose 1/2 of the maximum? Well, simply because it is halfway between maximum power and zero power. So it is easier to determine whether a signal is above or below that limit. Now remember that power is the voltage times the current, but the current is the voltage divided by the impedance. So this means that the voltage is proportional to the square root of the power. So we can equivalently define the cutoff frequency omega 0 as the frequency for which the voltage gain is the maximum gain divided by square root of 2. If we plug our expression of the real gain in that equation, we obtain this equation at the bottom, and I'll let you check that the solution is omega 0 equals 1 over R2C. This is our cutoff frequency. We could stop our analysis here, but if you want to understand what other people do or what datasheets about some circuit means, we have to mention that it is very common to define the gain in decibels as G sub dB equals 20 decimal logarithm of the voltage gain. So let us explain quickly where this comes from. First, from the properties of the logarithm, 20 log G is the same as 10 log G square, but G square is proportional to the power gain. So this is 10 times the log of the power gain. Why 10 times? Because we are talking about the decibel, 1/10 of a bell. A bell is a unit that is too big, so we like to divide it in decibels. Why do we take the logarithm? There are two main reasons for that. The first one is that it makes it easy to analyze the asymptotic behavior of the filter, but I won't discuss this here. And the other one is that our ears are more or less sensitive to the logarithm of the power and not the power directly. So to multiply the loudness of a sound by 2, we need to multiply the power by 10. All that being said, the important thing is the following. If we calculate the gain in decibels at the cutoff frequency, we find that it is equal to the maximum gain in decibels minus 3 decibels. So the thing to remember is that the cutoff frequency omega 0 is the frequency for which the gain in decibel decreases by 3 decibel. You will see those 3 decibels everywhere when you will read about filters, so this is where they come from. Finally, let us conclude the analysis of the low-pass filter by showing a figure that summarizes everything. What is shown here is the gain in decibels, and note that the horizontal axis is in logarithmic scale. At low frequency, the gain is maximum, and you can see that the gain loses 3 decibel at the cutoff frequency, as we predicted. At high frequencies, you can see that the curve becomes a straight line. This is precisely because we are working with decibels. In other words, what is plotted is the log of the power gain. It wouldn't be a straight line otherwise. You can also check that in the high frequency region, the gain loses exactly 20 decibels each time the frequency is multiplied by 10. We say that the gain decreases by 20 decibels per decade. That's what we call a filter of order 1. There exist numerous other types of low-pass filters that may be of order 2, for example, thus losing 40 decibel per decade. Let us analyze now a high-pass filter. The analysis is very similar to the low-pass filter, so now I'll go a little bit faster. We proceed in exactly the same fashion by noticing that again the circuit is very similar to the inverting amplifier, but this time the capacitor is in series with the input resistance. So the complex output voltage is minus R2 over Z1 times the complex input voltage, where Z1 is the series impedance formed by R1 and C, and we get the expression at the bottom. We define the complex gain exactly as before, and we write it in exponential form. The amplitude of the real signal is thus multiplied by the real gain G, and its phase is shifted by phi. You can check that phi is negative, but greater than minus pi, so this means that this time the output voltage lags the input voltage. From the expression of the gain, it is easy to see that it is maximum and equal to R2 over R1 when omega is infinite, and 0 when it is 0. So this confirms that what we have is a high-pass filter. The definition of the cutoff frequency is exactly the same as before. If we plug the expression of the gain in the definition, we find that omega 0 is 1 over R1C. Pay attention here, for the low-pass filter it was 1 over R2C. We use exactly the same definition for the gain in decibels, and the conclusion is again that at the cutoff frequency, the gain loses 3 decibel. So we can summarize everything with this plot. That's all for this high-pass filter. Now, an obvious way of making a bandpass filter is to merge the low-pass and the high-pass filters diagrams. So we have a series impedance Z1 instead of the input resistance R1, and a parallel impedance Z2 instead of the feedback resistance R2. I'll let you check that the complex output voltage is given by the expression at the bottom right. Deriving this shouldn't pose any difficulty. So we deduce the expression of the complex gain, and as is now usual, we write it in the exponential form, which shouldn't pose any problem either. Note the plus or minus sign in front of pi in the expression of the phase. You can choose the sign that you want since the phase is 2 pi periodic, but it is convenient to choose the sign that results in the value of phi in the range from minus pi to plus pi, because then the sign of phi tells us whether the output voltage leads or lags the input voltage. So, as for the low-pass and the high-pass filters, the amplitude of the signal is multiplied by G, and the phase is shifted by phi. The difference now is that we can define the resonant frequency as the frequency that maximizes the gain. As you should know, finding the maximum of the gain is determined by calculating the derivative with respect to omega and setting it to 0. This is certainly doable, but the calculation is much simpler if we realize that we can as well calculate the derivative of g squared with respect to omega squared. Once again, I assume that you know how to perform such a calculation, and you should find that the resonant frequency omega 0 is given by 1 over square root R1 R2 C1 C2. And the value of the gain for that frequency is R2 C1 over R1 C1 plus R2 C2. Another difference is that we have now two cutoff frequencies, omega plus and omega minus, and their definition is the same as before. They are the frequencies for which the voltage gain is equal to the maximum gain divided by root 2. So we have to solve the equation at the bottom. Solving this equation is rather easy, but a little bit tedious. I did it for you, and I suggest that you try to do it on your own, as it is a good exercise. Now, a quantity of interest is the passing bandwidth, delta omega, which is defined as the difference between the two cutoff frequencies. Surprisingly, the result is very simple and given by the expression at the bottom. The trick to arrive to this result is to calculate delta omega squared first, find some simplifications, and then take the square root. And here is the figure that summarizes everything. We can check that the gain is maximum for the calculated resonant frequency and that it loses 3 decibels at the cutoff frequencies. We can also check that the passing bandwidth is exactly as predicted, so everything is consistent. The last type of filter that we are going to discuss is the bandstop filter, also known as the notch filter. For some reasons, notch filters are usually a little more complicated because they usually involve more components. But here's one that is actually very simple, probably because it uses both a capacitor and an inductor. The analysis in this case is trivial because the op-amp simply works as a voltage follower. So all we have to do is to realize that the other components form a voltage divider. More precisely, we consider the voltage divider formed by the R1 resistor and the R2 LC series impedance Z. The gain of this divider is Z over R1 plus Z, and the exponential form of it is given at the bottom. Once again, you shouldn't have any problem to arrive to these expressions, but you can always review our chapter on complex numbers and impedances if needed. Now we want to determine the maximum and the minimum values of the gain, as well as the frequencies for which this happens. And in principle, we would need to calculate the derivative of the gain and set it to 0. But we can actually solve this problem in a much simpler way by reasoning directly on the voltage divider. It should be clear that the gain is maximum when the impedance Z of the R2 LC circuit is infinite. Clearly, this happens in both limits omega going to 0 and omega going to infinity, for which the gain is equal to 1. In a similar way, the gain is minimum when the impedance Z is minimum, which happens when the imaginary part is 0, thus when LC omega squared equals 1. This means that the minimum value is R2 over R1 plus R2, and it happens for the notch frequency omega 0 equals 1 over square root LC. As for the bandpass filter, we have two cutoff frequencies that are defined exactly as before. I give the expressions at the bottom left, and once again I advise you to try to derive them on your own as an exercise. We can define the blocked bandwidth delta omega as omega plus minus omega minus, and again its expression is surprisingly simple and given at the bottom right. Here are all the results of this notch filter on a plot, and this concludes this chapter on active filters with op-amps. There exist many more different configurations of filters, and obviously we cannot review them all, but the method of analysis that we developed is applicable to any of them, so you should be able to do it on your own. And should you encounter any problem with a specific filter, you can always message me about your problem. I hope to see you in the next part because we still have to discuss some other op-amp circuit.